So in the morning class, we were discussing about the Meissner effect and other related phenomena, like how the Meissner effect occurs in the superconducting material, how the superconducting materials are different from the uh, ideal conductors, and all. We are looking at in the morning session. So now we will just uh, look at the the type 1 type 2 semiconductors and how these are classified, why, what is the necessity of classifying. We'll just look at in this class. So we know that the magnetic field can destroy the superconducting properties, uh, because it will penetrate into the material and it will uh, break the super pairs, and as a result the superconducting properties can be destroyed or it is converted into the normal conducting state. So depending on the characteristics of the then superconductor may be classified into two types, right? Basically, type 1 and type 2. So most of the pure metals like lead, mercury, iron, and aluminum or comes under the type 1 superconductors. We will see what is type 1 and type 2. So the behavior of a long superconducting rod in an external field BA, what happens is small field are fully screened, that is a current or induced that generate magnetization acting opposite to the applied field BA. So that is mu BH. That means basically the magnetization in a superconductor depends upon the shape or shape of the superconducting materials. So depends upon the shape, the magnetic field that can penetrate into the superconducting material is different. So therefore, the influence of the external magnetic field on a superconductors is depends on the shapes, and it can be dictated by the shape of the superconducting materials. So that's what it is. Since the magnetic flux is completely expelled, we may rewrite this equation BA is equal to BA. This we have seen. This is what will happen when you, this is a case for the Meissner effect. So the intrinsic magnetic field that is associated will be equal to the applied magnetic field plus the magnetization. So that the net magnetization will be equal to zero now, because in the Meissner effect, that's what we have seen when it is transforming to the superconducting state. So basically, BI means the magnetic field or magnetic induction inside the sample. So in this case, BA is the intrinsic magnetic induction inside the sample, and M is the magnetization. So for the applied magnetic field, the corresponding magnetization will take place. That can be quantified using this relation. The resulting susceptibility. So if you apply a magnetic field, the corresponding magnetization M will take place, and as a result, we will also some susceptibility result of this that can be evaluated using this relation. So the magnetization, we know that B is equal to BA by mu naught. So B is equal to mu naught H. So BA is our applied magnetic field, and mu naught permeability in free space or vacuum. So, and using this, we can also calculate the susceptibility. We know the relation chi is equal to this. You might be knowing this is a chi symbol, which will be equal to mu naught permeability of the free space, and then our vacuum, then magnetization M divided by BA, applied magnetic field. So this net amount or the susceptibility, the net susceptibility or the calculated susceptibility will be -1 or -1. So this corresponds to the magnetic properties of the diamagnetism, right? Diamagnetic materials. We know that. Based on the susceptibility, we classify the materials into three types, basic, majorly. Apart from that, we also seen there are other types of magnetic materials, mainly dia, para, ferro, and in addition to that, ferri and antiferromagnetism all there. In addition to that, there are super paramagnetic and other properties also available. So in this case, we know that -1 is corresponding to the diamagnetic material. So this result expressing the fact that type 1 superconductors are ideal diamagnets. So because of from the calculations, we just get the susceptibility. That susceptibility gives us the gives an idea that under superconducting condition, the material behaves as a completely diamagnetic properties, or the susceptibility is in the zero or negative cases, or mainly the negative, because it expels, not even allows a feeble amount of the magnetic flux lines. Coming to this picture, how we are classifying the superconductors. So this is how we classify. How we classify? We apply magnetic field. We just look at the magnetization in a material. So based on the magnetization of the material, they exhibit different types of characteristics. Let us look at the first one, type 1, which are exhibited by some of the elemental superconductors such as lead, mercury, tin, and then aluminium. So what are those? Basically this. We just apply the magnetic field BA, just, and then you just look at the magnetization, which HC, basically the how the given material or the type 1 superconductors behave for this kind of material. So initially, we just look at this. Just initially, it is increasing. As you increase the field, what will happen? The slowly the magnetization will start, and it will reach the condition HC, critical field, at which the material completely behaves as a transforms into the the normal state. This is HC, the C, right? Critical field condition depends upon that this is the maximum. The critical field is a magnetization, and this is applied field. So this is the critical field. At this critical field, below this region, the material will behave as a superconductor. Above this region, or above this magnetic field condition, applied magnetic field strength. So this material will transform into the normal conducting state. So what happens here is slowly in this case, your magnetic field starts penetrating into the superconducting materials. Superconducting material, it starts penetrate. So, however, it was still at this magnetic field. What will happen? The Cooper pair will retain, or it will sustain until this point of critical field. Once it reaches this critical field, it starts slowly, not slowly, it is start splitting up into the free charge carriers. Instead of having the coulombically bound pair of electron pairs, they will just split into free charge carriers. So therefore what will happen, it will become normal superconductor. It will just behave like a normal conductors, from the superconductor to normal conductors. Okay, so this is this transition, the transition from the normal to the superconductor, or superconductor to the normal, will just occur very, very particularly very sharp applied field. It will takes place. That means the transition from the superconducting state to the normal conducting state, it will just occur in the very sharp critical field. So this is the case. The material which undergoes this kind of sharp transition, or exact critical field, I mean the sharp critical field, if it exhibits, they are called, comes under the type 1 superconductors, or the soft superconductors. So we will just look at the type 2 superconductors. What will happen? So let us take a type 2 superconductor. Usually we just take the material and analyze based on the applied magnetic field, then we classify. So if you take certain material and you just do the similar process, what you do is you just apply the magnetic field, and you just look at the magnetization -4 pi m, and you just see what's happening in this case, or a different critical field. Just calculate the critical field. So initially the field start penetrating into the superconductors, and certain point called the lower critical point. This is the first one, HC1. We just call it as a lower critical point. till this point, what happens? The superconducting state exists. So this is till this point, this will still will behave as an ideal superconducting state, and also until then, there won't be any penetration of the magnetic field into the superconducting material, or there won't be any magnetic flux lines inside the material, right? So until this state, or the till the lower critical, or the field is till the lower critical field, what will happen? The superconducting state will completely expel the magnetic field. So that is what we have seen in the Meissner effect, right? It will completely expel the magnetic field. Not even a small flux lines will be allowed into this. So what will happen until this lower critical field? These superconductors will behave as a superconductor, type 1 superconductors. Okay. So what I do now, after that, further I will again increase the applied magnetic field in the in this kind of superconductors. So what will happen? The superconductor still will act as a superconductors. However, what will happen? There will be some amount of flux lines, or some flux densities will penetrate into the superconducting materials, inside this kind of type 2 materials. The flux lines will start penetrating. So you can find out the magnetic flux lines in this region. Means if you apply the critical field, lower critical field, the upper critical field region, so there will be the penetration of the magnetic field that can be established through this relation. That is, you know the magnetization M, and you know the applied magnetic field strength, and you can calculate the susceptibility. And from the susceptibility of your material, we can just know that there is some field which are generated inside the superconducting materials. So this type of existence will takes place up to the upper critical field, up to the upper critical field. That is, HC2 is called the upper critical field. HC1 is called the lower critical field. So between these two regions, what will happen? There will be some amount of some intensity, or flux lines will be penetrating into the superconducting materials. In addition to that, the superconducting property will be still existing. That means it will behave as a superconductor, except that some flux lines will penetrate into the superconducting material. There will be some flux line. It will not completely expel the magnetic field lines. However, the resistance will be zero. That means R is equal to zero. It is electrical conductivity is ideally superconduct current. You will get a super current because there is no resistance. Resistance is still zero, but there is a small amount of flux lines that will penetrate into the superconducting materials, or the superconductor will allow certain flux lines inside this inside in it. Basically, in superconductor, it will allow some flux lines in it. So that will happen, or that will occur between the HC1 and HC2. Okay, now what I'll do is I'll further increase the applied magnetic field. Okay, BA I will further increase. So, so what will happen? My magnetization will further increase. So before that, we'll just look at there is something called theoretically calculated critical points. So practically, what we supposed to get is this H critical temperature in superconductor 2. So this is what we're supposed to get. This is the line, but it is starting from here and going here, reaching. But till this is a practically we are getting, and however theoretically we just predicted one is still the field will exist at this point, and then it's supposed to drop to this. That means at this point our normal superconducting to the normal conducting state would have we expected that this critical field. However, it is not happened. So this is thermodynamically favorable or theoretically predicted critical field for the type 2 superconductors. However, when you look at practically these type of superconductors, between the superconducting state and the normal state, there is something called the vertex state. The vertex state is the one where the resistance of the superconductor is zero. However, the flux density or the susceptibility values is not negative, or there is some kind of flux lines, or the magnetization will takes place in the superconducting material, or there is some magnetic flux lines will pass through the superconducting material, that will occur in the vertical state, that is basically from the lower critical field to the upper critical field, that in that regions. So further, in the higher further, if you increase the applied magnetic field again greater than hc2, basically higher further in the after the higher than the upper critical field, the superconducting state, basically the vertex state will convert into the normal state, which we know that basically this behaves like a normal conductor, where you have a resistance and also the flux lines will be magnetic flux lines will be penetrating into the superconducting materials. Basically, the normal conductors. It will turn into the normal conductors. This is the basic difference, and this type of superconducting properties we are mainly observing in the systems like alloy based superconductors, compounds alloy based conductors are the materials, or the intermetallic systems in superconducting materials, and other organic compounds. We can we can expect this kind of type 2 semiconducting behaviors. Okay, so basic difference is in the type 2 superconductors there is an additional state or the region in which yeah, the basic difference is in the between the type 1 and type 2 superconductors. In between the conducting and the normal conducting and superconducting state, there is some additional state is existing in the type 2 superconductors. But however, this is not happens, or it is not this type of existence is not there in the type 1 superconductors. So, because of the additional state exists between these type 2 superconductors, between the conducting state and the normal state, there are two critical field we need to come across, or we need to find out, or we are getting to evaluate or investigate this kind of superconductor type 2 superconductor. The main thing is the between the normal and superconducting state there is a vertex state exists. In that state, the magnetic flux densities are possible. I mean, the magnetic flux lines will pass through it in the in that particular states. This is one of the important questions you may expect in your final exam. So your exam is a descriptive type. So just concentrate on these titles. Type 1 and type 2 superconductors. So this is the major difference. Now we will look at the descriptions and whichever point we have left out. So the magnetization versus applied field for a bulk superconductor exhibits a complete Meissner effect. That is a perfect diamagnetism. So the superconductor with this behavior is called the type 1 superconductor. So the type 1 superconductor, what will happen? The complete set of the Meissner effect will be possible, or it will exhibit. So that means there is only two states: superconducting and normal conducting. So superconducting state, it will just completely behave as a diamagnet, or it is satisfying the Meissner effect. That means Meissner effect, we know that Meissner-Rosenfeld effect is basically the effect which tells us that under superconducting state, the material will expel the magnetic field when you apply the magnetic field to the superconducting state until the critical. That is also it will also expel until the critical field that we have seen in the previous class. There is a different critical field strength for the breaking the superconducting states. As you increase the field strength, the transition temperature also reduce. Instead of occurring in the 4 Kelvin, it will go to the 2 Kelvin in that, something like that. So basically, as you increase the field strength, your the transition temperature. That's what we have seen. So therefore, the type 1 superconductor behaves as a diamagnet, or it is exhibiting the Meissner effect, but this is not applicable to the type 2 superconductors, because we know that the Meissner effect is possible until the lower critical temperature, sorry, lower critical field, that is HC1, until HC1, right? Until this, the Meissner effect is applicable. That is, it is completely behaving as a superconducting state. After that, this is not the Meissner effect is not valid, or it is not exhibiting the Meissner effect. Between the HC1, lower critical temperature and the upper critical lower critical field and the upper critical field, the Meissner effect is not valid. That means the electric field, the magnetic fields are penetrating into the superconducting state. Therefore, type 2 superconductor exhibiting the Meissner effect until the lower critical, field. Between the lower critical and the upper critical field, there is no Meissner effect, or the Meissner effect is not a valid uh, discussion in this region, basically in the vertex region. That's why we just wanted to separate this region, because it is short of behaving like an ideal conductor with zero resistance, right? So therefore, this state we just call it as a vertex state. So in the normal conductor, what we assume is we have the zero resistance. However, the flux lines will penetrate into that. So sort of like this, not exactly, but sort of flux lines are penetrating. Therefore, we want to separate these regions from the superconducting state. We just call it as a vertex state. This existing between the superconducting and normal states. So therefore, the Meissner effect is valid until this one, HC1, the lower critical field. This region, the Meissner effect is not valid. So second thing, therefore, the superconductor with this behavior is called the type 1 superconductor. Above the critical field, HC, the specimen is a normal conductor, and the magnetization is too small to be seen in this case. So note that the minus 4 pi m is plotted on the vertical scale. The negative value corresponds to diamagnetism. So basically, the negative magnetization concept comes into the. We just want to mention or represent the diamagnetic properties. There is no physical significance. Sorry, this is just there is no mathematical significance. It's just a physical representation of significance. That means negative magnetization basically means we are playing with the diamagnetic samples or diamagnetic conditions. So there is therefore the minus sign in the vertical axis. You can just see here minus 4 pi m. This is again the minus 4 pi m. Just representing is there is no meaning for the minus 4 pi m. That means when you take into account in terms of mathematical representation, minus 4 pi m doesn't have meaning. It is just a physical representation that the materials are we are treating as a diamagnetic materials. That's what it means. Then the superconducting magnetization curve of type 2 superconductors, the flux starts to penetrate the specimen at a field of HC1 lower than the thermodynamical critical field HC. So that's what this is a thermodynamical critical field. Below this itself, the are supposed to penetrate in this position. The theoretically predicted values or thermodynamically calculated. The critical field value is this. However, this is not the case. It starts penetrating well below HC. That is, HC1 itself starts the lower critical, lower side, because this is lower than this. Therefore, just say as a lower critical field. This is above than the critical field. Just say as a upper critical field. So therefore, the magnetic field starts penetrating below HC itself. That means below this point. So that's the lower critical point itself. It's just start penetrating into the superconducting materials. The specimen is in a vertex state between Sc1 and Sc2, and it has the superconducting electrical properties up to Hc2. Above Hc2, the specimen is a normal conductor in the every respect except for the possible surface effects. For given Hc, the area under the magnetization curve is the same for the type 2 superconductors as for type 1. So this is the discussions which were doing till now, and we will also see. We were talking about the magnetic field which destroys the detects or destroy the superconducting properties. That's what we are discussing. Basically, the magnetic field can destroy the superconducting state of the material. In addition to that, we also looked at the uh, uh, not only magnetic field, the temperature also matters in in converting from the normal state to the superconducting and superconducting state to the normal transitions, right? So this transition temperature is dictated by also temperature. So how these magnetic field and the temperature are related to the critical field. That basically have taken this equation from different group for the explanation. For our according to our explanation, this is given in HC. This is given in yeah, basically is HC and HC. So just to understand this, and then if the external field is increased, the screening breaks down at the critical magnetic field called the BC. This is we know at certain critical field, the superconducting state will be no more existing. It will transform into the normal state. Transition to the normal state takes place. That is at the critical field that we are seeing. So the BC depends on the temperature. How this depends on the temperature? This also we discussed. Basically, when you have the field, you need to go to the very lower temperature. Then it will just it will transform into the superconductor without field. So that's what its curve is. This trend is same for all the curve. For a PB, in the morning we discuss PB we get around 7 at Kelvin, 7 Kelvin. Without field, it transforms to the superconducting state. However, if you increase the field to 20, millitesla, so it is short of transforming to this temperature, short of 6 Kelvin, right? So therefore, we need to go further 1 degree Kelvin, sorry, 1 Kelvin to achieve your superconducting transition temperature. So this is what we have discussed in the morning also. So then, for some type of this, note that all the simple superconductors exhibit qualitatively the same variation. Yeah, this is what. So we are. This is also we discussed in the morning. This trend is almost same for all type of superconductors. That means as you lower the that means as you increase the magnetic field strength from 0 uh, to higher values, the correspondingly the transition temperature also goes to the lower temperature regime or range or lower temperature region. So note that all the simple superconductor exhibit quality to the same variation. Simple superconductor means basically the elemental superconductors. There is no mixing of other elements, just the pure metals or semiconductors, anything. So only one element will be present in the simple superconductors. To enhance the to achieve the the transition temperature, higher transition temperature. That means basically we want a room temperature superconductor, right? That will be better to achieve. If you have that kind of superconductors, it will be better for our applications, various applications. So practically that is not possible. Only the superconducting state will exist at the liquid helium temperatures. It is better if you recently there are material like yttrium, barium, copper oxide, and other materials. People try to get the ITC is called. Looking for ITC materials. ITC means high temperature superconductors. Uh, So this type of material we wanted. So if someone found some superconducting materials at room temperature, they will give you the Nobel Prize. So note that all the simple superconductor exhibits qualitatively the same variations, which can be expressed approximately by the empirical relations. So so that is the relation, that is this. So how this is the critical field and then temperature functions, and this is the critical field when basically at zero, basically this is at zero, and how it is varying with temperature is 1 minus t by tc of square. This is how your critical field will be dictated. Just take the two functions, the magnetic field and then the temperature. Put these values, the critical field corresponding to that temperature can be calculated. If you want to calculate the critical field for a given temperature, you have to use this relation. You just put the values of, if you take the field at corresponding to zero temperature, what is the field? Just basically zero, right? At zero, what is the field? Just look at. So basically, so this is a critical field. We know for a given the superconductors, what is the transition temperature or the critical temperature, and we wanted to, we know at a given temperature what is the corresponding field needs to be calculated. That means at this temperature, what is the field we supposed to get our transition temperature. So, or the field which can breaks for a given temperature, or the field critical field which can breaks or which will transforms from normal state to the superconducting state or superconducting state, which is this can be this one, and this is for the zero temperature, and this is the temperature at which your superconductors are kept at. So this is the critical temperature of the superconductors, magnetic field BC versus temperature. So this is especially for the simple type of superconductors. The magnetization curve expected for a superconductor under the conditions of the Meissner-Rosen field experiment is given below here. So basically, yes, I think. So this applies qualitatively to a specimen in the form of a longer solid cylinder placed in longitudinal magnetic field. The pure specimen of many material exhibits this behavior. They are called the type 1 superconductors or a soft superconductors. The value of H are always too low for a type 1 superconductors to have applications in coils of superconducting materials. Usually, the field which can break the superconducting state or to achieve the superconducting state, or transforming from superconducting to the normal state or the reverse is very low for this case. That means with the low applied magnetic field, these superconductors will destroy in the type 1 superconductor will transform to the normal conducting material. So other material exhibit a magnetization curve of the form given below. They tend to be alloys or transition metals with high values of electrical resistivity in normal state. That is, the electronic mean free path in the normal state is short. So alloys and transition metals, metallic glasses, and novel HTCs are the number of families of type 2 superconductors. Usually, as I already told you, type 2 superconductors are alloys, transition metals, and metallic glasses, and novel ITC superconductors. These are mostly comes under the type 2 superconductors. So, as in type 1 superconductor, magnetic field is expelled until the lower critical field is reached. At higher field, the normal conducting islands are formed, allowing the penetration of magnetic field in the form of thin filaments, usually called flux lines or vertices. So this is and all we have seen between the superconducting and normal state. The flux lines will penetrate basically above the lower critical point and below the higher critical point region. So the normal conducting isolates are formed and allowing the penetration of magnetic field in the form of thin filaments, usually called the flux lines or vortices. Magnetic flux through these filament is quantized, each filament carrying the so-called flux quantums. So this is the usually the range of flux that will penetrate into the vertex state, the magnetic fields flux which can penetrate into the or the flux magnetic flux. Uh, the values of will be in this range, that is 10 power minus 5 Tesla per meter square. So basically in the vertex region, that is between the superconducting and normal conducting state, this is the usually the order of flex lines to this vertex region. The occurrence of two types of superconductors is usually type 1 and type 2, right? Is due to the fact that the energy needed for the formation of normal to superconducting interface is positive for type 1 superconductors, but negative for the two superconductors. So this is basically based on the energy formation, right? So the energy which is needed to make a transition from normal conducting state to the superconducting state is basically required is a positive one. Means the energy is we need to supply basically. Negative for a type 2 superconductor, maybe it expels out from energy is expelled or is released during this transition. So this is how just also can be differentiated based on the energy. The magnetic field in a type 2 superconductor as a function of applied field is shown in figure. That's what we have seen. And above SC1, magnetic flux penetrates in the form of vortices, and the field is only partially screened. After passing through the upper critical field SC to the material become normal conducting. That's what we have just seen. The magnetization rises with the field at low field as in the type 2 superconductor decreases above HC1 and vanishes completely at HC2. In this figure, the thermodynamic critical field BC is this thermodynamic critical field. Basically, this is H, right? In the figure, it is supposed to be HC threshold thermodynamic critical field. This field HC thermodynamically calculated critical field. So that is also drawn, and this is determined by the equations. That is upper critical field HC2 of type 2 superconductor may be several hundreds times larger than the critical field HC of the type 1 superconductors. Usually the upper critical field, right, the HC2 of type 2 superconductor may be several hundred times larger than the critical field HC of type 1 superconductors. So that means this one. This is the the critical field for the type 1 superconductors. However, in the case of the type 2 superconductors, the upper critical field, what we apply to break the superconducting state, is very much higher than this field which we require to break the superconducting, the field which required to break the superconducting state in the type 1 superconductors. That means this HC2 is greater than the HC, normal HC for the type 1 superconductor. That is why we just call it as type 1 superconductor, as a soft superconductors, because the very low magnetic field is sufficient to break the superconducting state into the normal conducting state. So this is the thing. The above passing through the plate. Above the magnetic field penetrating into this. Yeah. So the upper critical field SC2 of type 2 super may be several hundreds times larger than the critical field HC of type 1 superconductor. This is what we have seen. We also seen why that is soft superconductors, because very low magnetic field is sufficient to break them. To take an example, critical field for basically the HC2 is equal to 60T Tesla is found in the this compound, lead, gadolinium, uh, molybdenum sulfide. This type of a compound. We just need 60 Tesla to break the normal conducting state to the superconducting state to the normal conducting state. Basically, the upper critical temperature, the field, basically this field. This is basically comes under the type 2 superconductor. Around 60 Tesla we required to break this normal superconducting state to the normal conducting state in the case of this compound. The compound, Chaural compound, they call it as a Chaural compound. This is a lead gadolinium molybdenum sulfide. Another interesting class of type 2 superconductors are A15 compounds. The number of these classes niobium tin that has the relatively large critical parameters BC2, this upper critical field corresponding to zero temperature. We are not applying any temperature. I mean, basically the zero critical temperature. So, not critical temperature, zero of temperature. This is 25 Tesla, and the critical temperature for the applied without field is 18.7 Kelvin. So these are the two critical, the values for this. Basically, the critical magnetic field and the critical temperature for these niobium tin systems. This is technically important because of this compound can easily be processed and used as a material for wiring superconducting magnets. This is technically important because many of the superconducting materials are difficult to form a wire type of fabrications. This is difficult to form the wires because they are most of the superconducting materials are like a compound which are brittle in nature. Therefore, it is difficult to form uh, form the wires. So, in that sense, this niobium tin is the material or the compound which can one can use it for making the wires and use it for superconducting magnets. So why you need a superconducting wire? Because again, when you take certain current or some property you want to elevate, just you put a normal wires in the superconducting systems, you will end up with losing different parameters. Like therefore, the wires which we are employing or used for the superconducting based devices needs to be may, better to be used with the superconducting material itself. Both the critical field strength BC1 and BC2 depends on temperature. This is obvious. Again, the lower critical field and then upper critical field, basically HC1, and I will correct it and send when I send the PPT. It is supposed to be HC1 and BC HC2. The lower critical field and the upper critical field will be again depends upon the temperature. If you change the temperature, the corresponding field also will change, right? So that's again will be follow the trend of the like this type of trend it will follow again. So and they have their largest value at T is equal to 0, vanishes at T at the critical temperatures. The temperature variation of PC2 of several types given pictured. So we'll just see the figure here how this is varying. The critical field BC1 and BC2, basically SC1 and SC2, and then thermodynamical critical shown in the figure. Okay, basically this is the representation of different critical field and then corresponding variation of their field corresponding to the temperature, given temperature. So this is that. So this is similar to previously what we have seen in the morning. And with this, I will stop today. The Cooper pass and other will continue with in the next class.